In this section, we'll be talking about chi-square correlation, which could be used for testing between two categorical variables. You have seen chi-square in the Module 5 of Taxonomy, which talked about predictive analysis. Here we will get more in detail. Chi-square test examines whether the number of observations, or we say observed counts, within categories depart from expected counts for the corresponding categories. Here shows the equation of Pearson's chi-square correlation. Oj is the observed frequency, while Eij is the expected frequency. The expected frequency can be calculated through dividing the product of the respective row total and the respective column total by the total number of the observations. Here, the null hypothesis is the two variables you are testing are independent, namely, there's no relationship between the two variables. The test is based on a significance level, which with degrees of freedom. We will see an actual example in the following slide. Let's compute a chi-square correlation according to a real example. In this example, we want to investigate if there is a relationship between whether or not people taking aspirin and the geographical area they're in. Here we have two variables, aspirin taking and the geographic areas. The null hypothesis will be there's no relationship between the variables of aspirin taking and geographic areas. As shown in the table called contingency table in the slide, there are two levels for the variable aspirin taking and four levels for the variable geographic areas. Contingency table tells us how many subjects are in each category. For example, in the top left corner, we see there are 56 people observed taking aspirin in the area of Northeast. The number in the brackets represents the expected frequency, which is calculated through dividing the product of the respective row total, which is 338, and the respective column total, which is 276, by the total number of observations, 1,486. For each of the 8 cells, we calculate a result through dividing the square of the difference between the observed frequency and the expected frequency by the expected frequency. We add all of these results to get a final chi-square value. We decide whether or not this value is significant using the degree of freedom, which is calculated by multiplying the number of levels in one variable, -1, and the number of the levels in the other variable, -1. Here we have 4 levels in area variable and 2 levels in aspirin variable, such that the degree of freedom is 4 - 1 multiplied by 2 - 1, which is equals to 3. There is a table for you to look up the significant chi-square value for a degree of 3. And in most of the programs, the value will be automatically looked up and the p-value will be calculated. As long as your value is larger than the reference value at the corresponding degree of freedom and significance level, you should be confident to reject the null hypothesis. For a 3 degree of freedom and at a 0.05 confidence level, the chi-squared value needs to be larger than 7.8147 to reject the null hypothesis. As we have calculated, our value is 14.11. That implies the result p-value will be less than 0.05. We could reject the hypothesis, the null hypothesis, and two variables appear to be related. The chart used for visualizing a chi-square test could be a bar plot. Along the horizontal axis, we have categories of one variable. The different color of bars represents the categories of another variable. The numbers on the vertical axis show the observed frequency inside each group. You can also do it inversely to have 2 groups of bars and 4 bars within each group. Okay, that's all for this section of chi-square. Please answer the following questions.